Okay, so we need to find the magnetic field over here at wire A due to the other two wires in order to find the force. Let's start with wire B. The right-hand rule for wire B, if you point your thumb in the direction of current for wire B, then your fingers will go into the page on this side and they'll come out of the page over here. So that's the magnetic field due to wire B. For wire C, it's the opposite. If you point your thumb down, then the magnetic field on the left side of the wire will go into the page, and on this side of the wire it'll come out of the page. Okay, so that means that wire A is immersed in two different magnetic fields. Okay, it's immersed in the magnetic field due to wire C, which points out of the page. Magnetic field due to wire B, which points out of the page, and the magnetic field due to wire C that points into the page. Okay, and it feels a force, and that's true on both sides, right? I mean, it's immersed in that field. Okay, this is BC, right? Because there's just basically a forest of X's due to wire C that exists in this whole space all over here to the left of wire C. They just get weaker the further away you get from wire C. And likewise, there's a forest of little dots to the left of wire B that exists all out in this direction. Okay, so that's the magnetic field that wire A is immersed in. Now, to find the magnetic force on wire A, we have two choices, right? We can do LIA cross BB plus LIA cross BC. Okay, we could find those two magnetic fields and add up those two forces in a vector way. Or we could write it as LIA cross B total. Okay, why don't we just do that and save ourselves the trouble. So to find the total magnetic field, let's start with the magnetic field due to wire B. That has a magnitude of mu naught IB over 2 pi times 0.35, which is 3.2 microtesla, sorry, 2.5 microtesla, pointing out of the page. And then the magnetic field due to wire C, distance here is 35 centimeters plus 21 centimeters, which is 0.56 meters. So that's 3.2 microtesla, and that points into the page. So the total magnetic field, if we take this, if our sign convention is that out of the page is positive and into the page is negative, the total magnetic field would be plus 2.5 minus 3.2, or 0.7 microtesla, negative 0.7 microtesla, right? Or if you want to put it this way, 0.7 microtesla into the page. Okay, so the net magnetic field, the total magnetic field, is rather weak, but it points into the page. And if that's the case, the right-hand rule tells us, right, if we do magnetic force is LIA cross B total, tells us we use palm, thumb, fingers, right? So if you point your thumb in the direction of the current and your fingers in the direction of the magnetic field, total magnetic field, then your palm is going to point in this direction. So there's our force. There's our magnetic force. It's going to point to the left. Now, to find the force per unit length, I just take the current multiplied by the total magnetic field, which is 0.7 microtesla. Sine 90, I guess. They're perpendicular to one another. And that gives me 1.8 times 10 to the minus 6 newtons per meter, and it's directed to the left.